Welcome to the talk about the paper with the title When Lipschitz Walks Your Dog, Algorithm Engineering of the Discrete Fréchet Distance Under Translation. This is joint work with Carl Bringman and Marvin Kühnemann, and my name is Andre Nusser. Before I actually start giving the full talk, I want to give a quick teaser such that you can decide if you want to watch the remainder, which of course I hope. So this work is about trajectory similarity. Here you can see pigeon trajectories, a clustering of it, or handwritten characters, which you might want to classify. And in these scenarios, you actually want to have a similarity measure, which usually requires the usage of the Fréchet distance if the points are ordered. At least that's the most popular measure. It's traversal based and it's also fast in practice. And normally it's explained by a human and a dog, which are connected by a leash and walking alongside those trajectories. And then you want to minimize the leash length that they have, and they're only allowed to walk forward. Later I will give a better definition, but this is just for the teaser now. Unfortunately, the Fréchet distance is not traversal translational invariant, but the Fréchet distance under translation is translational invariant. So what does it mean that it's not translational invariant? It means that if I move one curve, then actually the Fréchet distance changes. But if I'm only interested in shapes, like for characters, then I want something translational invariant, and that's the Fréchet distance under translation. But the issue there is that until now there were no practical algorithms, and this work changes that. So why were there no practical algorithms? Well, in theory, the best known algorithm is n to the 4.66, which is actually quite slow in practice. And there's even a conditional lower bound of n to the 4, which matches the size of the arrangement. And the arrangement here of this problem you can see here as an example. So it's disks with same radii. But the good thing about the Fréchet distance under translation is that it's one Lipschitz in tau. So if you have the translational space, and now you put the value of the Fréchet distance there with this specific translation, then you can actually optimize this using methods from continuous optimization with a branch and bound approach. Unfortunately, this is only approximative, but if we combine it with the arrangement-based approach, then we get our approach, which we call Lipschitz meets Fréchet, and there we actually do both. So let's look at the rough results that we get in experiments. So the runtime is something like 100 milliseconds on a character dataset, and we outperform the arrangement-based algorithm by a few orders of magnitude. The take-home message is that combining an arrangement-based geometric algorithm, which is exact but expensive, with methods from continuous optimization, which are approximative, we get a fast practical algorithm, which is exact. So that's the rough overview over the talk, and now I will actually go through it slower and explain the details. So why trajectory similarity? As I already said in the teaser, if we, for example, have pigeon trajectories, and those are real pigeon trajectories here, and it's a clustering from it, then to cluster them, we need some notion of trajectory similarity. And the same for handwritten characters. So if we want to, for example, classify them, or if we want to find out what are the different shapes, so here you can see different shapes of G, then we want some notion of trajectory similarity. And one measure which captures that is the discrete Fréchet distance, and it's explained by the human and dog, and they are connected by a leash, which you can see here in orange. So they both start in a starting point, and then there are three possible moves that they can do. So first, both can jump to the next vertex because it's discrete here, or the human jumps to the next vertex, or the dog jumps to the next vertex. And like this, they can traverse the whole trajectories until they are both in the last node. And now we ask ourselves, what are the traversals such that the leash length is minimized? What is the leash length? The leash length is the longest distance that they have during the traversal. So this would be the leash length here. Okay, so that's the Fréchet distance. Let me give a more formal definition. The Fréchet distance of two curves pi and sigma is the minimum over those legal traversals, which I just explained. So either both jump forward or only one jumps forward. And what are we minimizing? We minimize the leash length here, which is the maximal distance that the dog and the owner have during the traversal. With n, we denote the length of those polygonal curves, and just for simplicity, we often assume that they have the same length, but this is just for simplicity. So the implementation also works for curves with different lengths. Now, if you want a translational invariant version, then there's actually the Fréchet distance under translation. And there we have a translation. So we minimize over all translations. And what do we translate? We translate the second curve here. And we want to know the best translation such that the Fréchet distance is minimized. That's the Fréchet distance under translation. So let me show a picture here. Again, we have the human and the dog. The dog is very stubborn, so the dog won't change its path. But the human is just a bit stubborn, so the human just wants to keep the shape of its path, but actually the starting point he or she can choose arbitrarily. So we can translate this whole curve, and we want to know what's the best translation such that the Fréchet distance between those two is minimized. In this work, we mainly consider the decision problem, or rather, actually in this talk, we mainly consider the decision problem. So we are given two curves, pi and sigma, and then a threshold delta, and we want to know what is the, so we want to know if the Fréchet distance under translation of those two curves is at most delta. Good. So the goal of this work was to get a performant implementation computing the discrete Fréchet distance under translation on practical inputs. And in the remainder of the talk, I will explain how we reached that goal. So let us first review a little bit the related work. In theory, I already briefly mentioned it at the beginning. We have results already, and especially we had this n to the 5 algorithm. There were previous results, but I just restricted a bit. So we had the n to the 5 algorithm by Agarwal, Ben Avraham, Kaplan, and Sharir. And we improved that actually to n to the 4.66 and also gave a lower bound, a conditional lower bound of n to the 4, which matches the arrangement size, as I already mentioned. So unfortunately, this is quite pessimistic in practice. We want something better, but yeah, let's first review how practice actually looks like for the fixed translation Fréchet distance, because for the Fréchet distance under translation, there was, to our knowledge, no practical work actually. So in the GIS Cup, it was about computing the Fréchet distance as fast as possible, or finding near neighbors actually, and those were the organizers, and those were the 3 winning submissions. And this was already a very nice step forward for engineering the Fréchet distance. And then we actually gave a state-of-the-art implementation in a Sausage 2019 paper for the fixed translation Fréchet distance. And actually, this work here, we will also use as a subroutine in the remainder. And I will tell you then where. So there are actually 2 approaches that I want to talk about. The first approach is the classical approach that you have in discrete geometric algorithms. And this is building an arrangement. So I will quickly explain how we built this arrangement. So we have those 2 curves here. And now in which case does this point here get close to this point? It will get close if this point is translated into the delta ball around this point here. So here you can see delta. Okay, so we see here the coordinate system of translations. So we transfer this ball here into this coordinate system. So if we choose a translation somewhere inside here, then those 2 points will get close. And the same we do for the other 2 points here. So again, we transfer it to the coordinate system, and those we now do for all pairs of points of those 2 trajectories. And then we reach the arrangement. Now the observation here that was already made is that all translations in a single cell, for example, this here would be a single cell. All translations here, the pairs of nodes have the same closeness or farness. So basically, if those 2 nodes are close, for example, for this point here, then you also know that they are close for all the other translations here. And using this, we can actually just pick an arbitrary point from each cell. For example, we can also just pick the intersections here, all the intersections, and check them for the Fréchet distance. And if we try them all out, then we get a decision of the Fréchet distance under translation. The problem here is that this arrangement actually has an O(n to the 4) complexity. And that's an issue in practice. Now, let me show you how bad actually an O(n to the 4) arrangement can be. So we have those 2 curves here, and they actually have significantly more nodes, but we removed a lot of nodes to simplify them. And the arrangement still looks like that. And you see, especially here in this area, it looks very bad. I mean, there's a lot of intersections, there's a lot of cells, and we have to check a lot of points here. So that's not very good. We need some other approach to help us out here. And the second approach that I want to talk about is the one of continuous optimization. So here again, you see two curves, but now we take this translational space here. So these are all the two-dimensional translations, and we just plot the Fréchet distance, the value of the Fréchet distance with this translation here. And we can see that this actually looks pretty smooth, right? I mean, it looks even almost convex. Unfortunately, it's not really convex, but it's globally already quite good. But why does it look that smooth? It actually looks that smooth because the Fréchet distance under translation is 1 Lipschitz. That means if we take a translation and the Fréchet distance there, and another translation tau prime and take the Fréchet distance there, then their difference is at most the difference of these two, or the norm of the difference of those two translations. So that's very nice. And therefore, we can actually use Lipschitz optimization. And in Lipschitz optimization, one common approach is to use branch and bound. So I will quickly explain the algorithm because we later use it. So in this algorithm, we start with a restricted area that we somehow have to compute, but I won't go into detail here. You can see that in the paper. So we start with a box here. And what we do is we check the middle point. And for the middle point, we want to know if the Fréchet distance with this translation is at most delta. And if so, then we can return less, right? Because then we found a witness and we are actually done whenever we do that. And here you already see that we have to use the fixed translation Fréchet distance. So that's what we use the Sausage 2019 implementation for. So we have these black box calls here. And we also have a negative filter in Lipschitz optimization. And there we check if the Fréchet distance at this point is larger than delta plus the length of this diagonal. Because if this is the case, then that means that all the values here in this box will be larger than delta, and we can skip the box. But we cannot completely return, but we can skip the box. Because we do this for all boxes, and if none of these two are the case, then we actually have to split, and we just recurse on the boxes. So that's the Lipschitz optimization framework that we use. Now, the issues are that this can only give us approximate decisions, because you might actually go into an infinite recursion. And of course, this is an issue if you want to implement things. The other issue is that it can be locally highly non-convex, right? So on global scale, we saw that it's actually quite nicely convex. I mean, that's not generally the case, but for practical inputs, that's actually quite common. But locally, this is a practical input. Locally, it can look like this. And that's a huge problem, because now we have to actually explore all the different areas here. And also the lower bounding doesn't work very well. So this is an issue. How do we get rid of this? Well, we combine both approaches. So how do we do that? We use continuous Lipschitz optimization to identify important regions. And then we use an arrangement-based approach to actually decide completely inside these regions. And because the original arrangement is large, we hope that the local arrangement is significantly smaller, and in the experiments you will actually see that this is the case, that we actually don't have to build large arrangements anymore. Okay, so this already brings me to our first contribution, which is an exact decider. So the approach of this exact decider is that we augment the branch and bound approach of the continuous Lipschitz optimization, such that for each box we estimate the arrangement size, and if the arrangement is small, then we can build the arrangement, because then also the algorithm is fast, the discrete geometric algorithm. And this gives us an exact decision, which is very nice. So now let me explain how the algorithm works. So here on the right side you can see a visualization. So here the Lipschitz optimization approach actually didn't find anything, and also the arrangement was large, so we split the box, and here then we again split the box. But now for this box, actually our arrangement estimator said, okay, the arrangement is small, and if it says that it's small, then it will always be small. So we can actually now build the arrangement here, and we evaluate all the intersections, but here we can see that actually all the intersections are negative. So unfortunately, we didn't find a witness, so we have to really continue searching, but at least we're done with this box. And that's the good point, without building a large arrangement. So we continue and we actually see, oh no, all the box here boxes here, we don't have any solution. And for this box, we again estimate that there's a small arrangement. So these are all excluded by the Lipschitz optimization, by the way. And here again, we build the arrangement. And then we find this node here, which is actually positive, and we can return yes. But important here is that even if this node here would be negative, then still we could stop because we explored the whole search space and we are done. And we don't have to go into an infinite recursion where, for example, we have to now split here over and over and over again to search for a solution, even though there is none. Okay, so that's the exact decider. So the main issue here is when do we actually build the arrangement, and we have to somehow have an arrangement size estimation, and we have to have a threshold parameter when we actually do build it. So the arrangement size estimation we do through a modified KD tree where we put all the disks of the arrangement and then we get an estimation of the size, and the threshold parameter we empirically choose. So just a few implementation details. As I already mentioned, actually we use an adaptation of the Sausage 2019 implementation. So why do we have to adapt it? Because it was actually just for the continuous case, and now we need to have it for the discrete case. Know that we're talking here about a fixed translation Fréchet distance, not under translation. Okay, so this was one of the part that we had to do. Then also we do a lazy translation, which means we don't just, because if we evaluate one point in the translational space, then we need to translate the whole curve in theory. But in practice, it might actually be that the first two nodes, for example, are already further than delta, and then we wouldn't even need to compute the Fréchet distance further because we already know that the Fréchet distance is larger than delta. So we do a lazy translation, therefore, and we just translate the points when it actually becomes necessary, when the algorithm actually accesses those points. And then we also need to think about the parameter choice for the arrangement size estimation. And as I already said, this we do empirically, and this offers quite some interesting future work, how one best chooses this parameter. And the estimation, by the way, we do just by looking how many circles intersect this box, and then we can give an upper bound on the arrangement size. Good. So this actually leads us to the second contribution, because now we have the decider and we want to turn on value computation. So we want to approximately compute the discrete Fréchet distance under translation. And there are a few natural approaches now. One is just giving an epsilon set. So we just put a grid over the possible region, and then we evaluate each point here in the grid, and then check if the Fréchet distance there is at most delta or not. So unfortunately, this is huge in practice. It's 1 over epsilon squared. So if you choose a small epsilon, then this is just infeasible. So we didn't even do experiments there because it wouldn't have terminated anyway for small epsilons. But a very natural approach is now to use the decider, because we already have a decider, right? So we can use a decider and just do a binary search over delta using that. And actually we will see that in the experiments that this is quite good, but we can do better. Another option then also is to use Lipschitz only optimization. So in the approaches at the beginning, I actually talked about the Lipschitz only optimization, and we can actually only use that here. And we will also see experiments for that, but definitely we expect that the other approaches would be better, which is also the case. And our new approach now is the Lipschitz meets Fréchet. So this is also, of course, also a new approach, but a modified approach which specifically is tailored to the value computation is what we call Lipschitz meets Fréchet, and I will explain it on the next slide. So it's somewhat similar to the decider, but there are some very important modifications that one has to do. So now we have to maintain a local lower bound. Why a local lower bound? Because we just want to know if we can stop searching in this box. That's why we have a local lower bound, but we want to maintain a global upper bound. So for example, if we already found a small value somewhere here and we're still exploring a box somewhere down here, then we can easily know that, well, there's a good solution here. Why should we explore further here? So the lower bounding with this diagonal will actually work much better if we already have a good upper bound somewhere else. That's why we have a global upper bound. And we also need a different arrangement size estimation, because now we don't have fixed radius disks anymore, but we have disks which are in between radii, so we have to modify the KD tree again. Unfortunately, I cannot really go into detail here, but it's in the paper, so I suggest you look into the paper for that. Now for each box here, we want to now get a global upper bound. How do we get this? Well, we just again evaluate the midpoint and then we take the minimum. We want to get a local lower bound. For this, we do something similar as before in the lower bound. So we evaluate it and we subtract the diagonal here, and this gives us a lower bound on all the distances in the box. And now if the upper bound is still too far away from the lower bound plus epsilon, then we have to split and search for further. So in this case now, we then, if we build the arrangement, so here again, let's say we in the arrangement size estimation, we actually found out, okay, this arrangement is small in the modified version, then we still have to get the value somehow, so we do a binary search over the arrangement. Good. So again, there are some implementation details. Again, the arrangement size estimation, I already mentioned what the issue is there, and for the details, please look into the paper. Then also initial estimates. So we have to get some initial upper and lower bound, and this we actually get by matching the starting points and the ending points, because they definitely have to be matched to each other, and then we take the better of the two, and by that we get a very good upper and lower bound already at the beginning often. And what is very important is that now we actually have to decide in which order do we explore the boxes in the branch and bound strategy. And what we do is we explore it in increasing lower bound of the boxes, which is a no regret strategy. So even if we know the value already, then we still would have to explore the boxes just to find the spot where the minimum is actually realized. Good. We also did some experiments on a 6 spatial data set and on the characters data set. And here you can see the different properties of those data sets. But I want to go in the experiments right away. So here you can see this plot shows, so this is the optimal distance. So we test the decider, and here we can actually see the actual distance between those two curves, the actual distance under translation. But we want to check the decider, what happens if we are slightly below the distance or slightly above the distance. And you can already see here that actually below the distance, it's much harder, but we're still at a time of something like 80 or 100 milliseconds, which is pretty good even for the difficult instances here. So for the 6 spatial data, it looks quite similar. There are still also we get times which are in the range of something like 300 milliseconds. And again, those are the difficult cases. So I already mentioned those 2 points here. Good. So let's have a look at other experiments. Here we plot the number of black box calls. So those here are the number of black box calls that the arrangement-based approach would need. And here you can see it's a logarithmic scale. So it's something around between 10 to the 6 and 10 to the 7. And here, even for the hard instances, for the easy instances, it's much lower. But for the hard instances, it's just here, somewhere between 10 to the 3 and 10 to the 4. So we outperform the arrangement-based approach by a few orders of magnitude. So this didn't even work in practice, but ours now works quite fast in practice. The same picture we can actually see for the 6 spatial data set. So yeah, that I already mentioned. We are several orders of magnitude faster in the sense that we have significantly less black box calls to the Fréchet decider. Now here we compare the approaches for computing the values. So we have Lipschitz meets Fréchet, so our new approach, and the binary search and Lipschitz only. And here you can see binary search is something like a bit more than 3 times slower than Lipschitz meets Fréchet, and Lipschitz only is something like 8 times slower than binary search. So we, from Lipschitz only to Lipschitz meets Fréchet, we have something like a factor of 25. So that's also pretty good. And let's look at the last experiment. Here we compare how the binary search performs versus Lipschitz meets Fréchet, and especially here we map the times onto each other. So the interesting thing to see here is that here for small times of binary search and a bit larger times for LMF, we actually get quite some instances where binary search is faster than Lipschitz meets Fréchet. But for the hard instances, which you can see here, so this is the diagonal is the identity. So for the hard instances here, it's actually below the diagonal, which means that Lipschitz meets Fréchet is significantly faster, something like 1 order of magnitude faster than binary search, or yeah, something along those lines, or maybe factor 5. Yeah. So that's pretty good, because that's what we're trying to optimize for. We try to reduce the running time for the hard instances. Now, let me summarize. What we saw is we have an arrangement-based geometric algorithm, which is exact but expensive. We have methods from continuous optimizations, which unfortunately are only approximative. But if we combine them, we get a fast practical algorithm, which is exact, which is very nice. And actually, in future directions, what is very interesting is, can we actually apply the approach to other problems? And that is, for us, that's the main point actually of this paper, is that maybe we can actually use this for other approaches. And we should look at other, especially geometric problems, where this is possible, and this might give significant practical improvements in this area. And another thing that is open is to finding the optimal point when we actually build the arrangement. So if we have a good estimation on the arrangement size, when do we actually want to build the arrangement, and when do we want to continue searching still? So this threshold parameter there, or maybe even not choosing a parameter but something else. So that was all. Thanks a lot for listening to the talk. And the code is, as always, public. You can find it on GitLab, and the link is also in the paper. So thanks a lot.